I work for that company. We're recording in progress. Great. I work for another company called Impervious. We are also making a browser. It's different. It's going to be confusing. I work on another blockchain project called Handshake and also on Bitcoin. My contributions to Bitcoin, I've made a couple commits to Bitcoin Core. I do a lot of education and participation on Stack Exchange. And primarily, I'm a maintainer of the Bcoin code base, which is a full node and Bitcoin library written in Node.js. And my students for this summer are going to be focusing on Bcoin and adding some features to it. So let's get into it. The plan for the day is to explain basic Bitcoin concepts. I know everybody has a range of knowledge about Bitcoin and computer science already. So the point of today's talk is to inform and educate people who are just learning about Bitcoin, but are developers who understand how computers work and networking and programming and stuff. We're going to teach you some basic concepts about Bitcoin. And for those of you who already know these concepts about Bitcoin, you might find these explanations helpful in explaining Bitcoin to other people, because I'm going to try to break it down really simply using things that most people already understand about technology. And I gave this talk last year, and I also basically gave this entire talk to my cousin who visited me last month. She's 10 years older than me. She's an interior designer. And she was like, all right, I finally got you at a dinner table. Let's talk about Bitcoin. And I basically gave her this entire talk as you're going to hear it. And it worked out really well. So if you're explaining Bitcoin to other people, you might find some of these metaphors useful. The technical terms I'm going to offer are not like official. This talk is kind of self-contained. I'm just hoping to inspire you to go down these different rabbit holes and actually learn how most of these mechanisms really work. And that's what this summer is going to be all about. But hopefully this will give you the basic concepts about the important things about Bitcoin. Okay, what is Bitcoin? Somebody asks you, what is Bitcoin? Usually I respond by asking them, what is email? That's something that basically everybody knows. You can define email 3 different ways. I like to define it these 3 different ways. It is a unit of correspondence, like I have sent you an email. I got an email today. It's a unit. It's also a computer program. There are lots of different options for running, different types of computer programs that do email. You can use Outlook, Thunderbird, Gmail. And finally, it's also a networking protocol where those computer programs I mentioned in number 2 connect to each other on the internet and do email together. The protocol is technically called SMTP. Protocols are things that have sets of rules. For example, emails must have a from and a to, otherwise it's not an email. You're not following the protocol rules. So we can use those 3 definitions to also define Bitcoin. The word Bitcoin has these 3 definitions. It's a unit of value. That coffee costs, 0.01 Bitcoin, or I get paid in Bitcoin, or I have Bitcoin here and there. Bitcoin is also a computer program like email. There are multiple computer programs that do Bitcoin. Bitcoin Core is obviously the most popular, most dominant. There are alternatives like Bcoin and BTCD and others. And then finally, Bitcoin is a protocol where computer programs running on people's computers talk to each other on the internet, following a certain set of rules to do Bitcoin together. So email servers connect to other email servers and follow certain rules to maintain a unique database for each user. Here I've got Homer, Bart, Nelson, and Lisa, and they're each running email on their computer, and their email programs on their own computers maintain a database for that user. Bart has Bart's database, Lisa has Lisa's database. Their databases are different from each other because Homer doesn't need Bart's emails and Nelson doesn't have access to Lisa's emails. So this is how it looks. Everyone's got a unique database, but the computer programs are all talking to each other. We have these protocol rules. So here Bart is sending Homer an email with a to field, a from field, a subject, and a message. That's great. You're following the rules. You have sent an email. Nelson, however, is trying to send Homer a message that has a to field, but then a bunch of garbage, and it's missing a from and a subject. And just because that message is breaking the rules of the email protocol, Homer's computer is going to ignore it or reject it, or maybe even ban Nelson by his IP address or something like that. Rules are important for a protocol to work. Now, the thing that we're going to do with Bitcoin that's very different from email is we want everybody to have the exact same database. That's because it's a monetary accounting system. Everybody needs to know what money is real, how much money there is out there, where the money is, which, if I'm going to send you money, you want to know that that money is real, that you will be able to send it to somebody else. So we need everybody to have the exact same database, and that's going to be our goal for today. So let's start a bank. Everybody on this call is a computer programmer, has some experience. We are going to write a bank computer program, starting with the database. And if you think about it, this is really all we need. This is as a bank is just this simple. You have one table with data sorted by users. Each user has a password and a balance. Super simple. A transaction modifies the database in this way. So you can imagine a transaction comes in from a user with a username Bart, password don't have a cowman, recipient is Lisa, and the amount is 2. We do 2 checks. First, we check that the password is correct. It is. Then we check that Bart has a balance greater than the amount he's trying to send. He does. This is a valid transaction, so we will mutate the database in the way that I've illustrated here. So Bart's balance goes from 15 to 13. Lisa's balance goes from 100 to 102. Super simple. Banks are easy. Where bank programming gets challenging is this guy right in the middle, this password column. It's incredibly sensitive, right? It can't be public. It can't be shared. We have to keep it, in a vault underground, protected by guns and dogs, and we can't let anybody in there because this is the weakest link in the whole system. If Homer gets Bart's password, he can send transactions and steal all his money. And so we end up with an architecture that looks like this. There's really only one database. It's at the bank. It's very, very safe, and users can send transactions, but it all has to go into this one database. Centralized, authoritative, censorship prone, blah, blah, blah. Okay, so now we're going to start to get things interesting. I don't see anybody having any, the passwords are in plain text. Good catch, Crystal. Well, now we're going to talk about cryptography, so maybe you can help us make our banking software a little better. I'm going to talk about a couple cryptography definitions. If you already know how cryptography works, these are going to sound maybe wrong to you. But again, we're just talking about the concepts. We are explaining cryptography to my 50-year-old cousin who's an interior designer. We want her to understand. I'm also going to describe some cryptographic principles that are not used in Bitcoin, like symmetric encryption, because a lot of people will misuse the term and they'll say, oh, this thing is encrypted on the blockchain. And after a couple more slides, you will be able to correct that person and say, no, actually nothing's encrypted on the blockchain. We don't use cryptography for encryption. Okay, here's a couple cryptographic terms that I basically kind of half made up. First one, symmetric encryption. Symmetrical because there are 2 keys, they are identical, they are symmetrical. In this illustration, Bart and Lisa have the same key. Bart is sending a message to Lisa. He takes the message, combines it with the key somehow, and the output is this random noise. If Nelson's looking at it, he can't tell anything about the message. It's just this random noise. However, Lisa has the exact same key. She can subtract the key, get the original message out. I have a little sister. When we were in school, she used to pass notes to her classmates about which boys they had a crush on, and they were basically encrypted using symmetrical encryption. They had a key, which was the English alphabet, where each letter was replaced by a symbol. Her friend Lori had the same key. They could send encrypted messages that way. I, of course, hacked the key and was able to figure out who my sister had a crush on. So this is symmetrical encryption, not used in Bitcoin, but let's talk about it. Okay, asymmetric encryption, starting to get a little more interesting. The math gets way more complicated. Here, there are 2 keys. Bart has one key, Lisa has the other key. They are somehow related. Bart can encrypt a message to Lisa. So Bart has the public key. He can take a message and encrypt it. Again, it turns into random noise. It's undecipherable. Nelson has no idea anything about the message. It's just random noise. Lisa has a different key. She can use that key to decrypt the message. So Bart cannot decrypt the message. Nelson cannot decrypt the message, but Lisa can. This is, how Edward Snowden sent messages to Glenn Greenwald about terrible things the United States government was doing. Glenn Greenwald's public key is very easy to find. It's on the internet. You can take that public key and encrypt data or encrypt a message to Glenn Greenwald and send it to him with the confidence that only Glenn Greenwald can decrypt it and read the message. Asymmetric encryption, 2 keys, they're different. That's why they're asymmetric. Not actually used in Bitcoin, but we're getting closer. Okay, asymmetric authentication. This is definitely a term that I made up, but it sort of follows with how I've described the other 2 principles so far. So we still have 2 different keys, but in this case, we're not actually encrypting the message, we are signing it. So Lisa has a private key, Bart and Nelson have the corresponding public key. And what Lisa can do is take a message and use her key to add a signature to it. And then Bart and Nelson can take the message and the signature and the public key and verify that the message was signed by Lisa. We assume that Lisa is the only person in the world who has the private key. Therefore, if we see a signature that is validated by her public key, we can assume Lisa created a message. This is, again, so if Glenn Greenwald wanted to broadcast a message or send you a message, he could use that same public key and sign it. And you would know that, under the assumption that he's the only person who has a private key, he must have created that message. He signed it. Okay, asymmetric authentication. Asymmetric because there's two different keys that aren't the same. Authentication because we're not encrypting data, we're authenticating it. And this is definitely used in Bitcoin. This is a big one. And then finally, hash functions. There are no keys in hash functions. What a hash function does is it takes some type of data, any amount of data, any size of data, and distills it down to an output. The output of a given hash function is always the same size. Good hash functions, the outputs are impossible to predict, and there is no way to reverse them. But it always is the same every time. So I really love the chemistry set emoji for this metaphor because it really explains what's going on. You can put anything in there, any amount of ingredients. You can put in a single byte. You can put in all of Wikipedia, and you boil it up with chemistry, and out comes one single drop. And from that drop, you cannot have any idea what the original ingredients were. But theoretically, if somebody were to do the exact same experiment, they would distill it all down and come up with the exact same result, even though it's tiny. And you can put, 1 ounce of water in there and you get 1 dropout. You can put all of Wikipedia in there and you get 1 dropout. They're always the same size. So in this cartoon, Bart and Lisa have the same data and the same hash function, and they get the same result. So if Bart gives Lisa this hash, Lisa can verify the hash by putting in the same data into the same hash function, getting the same result. Nelson, however, has different data. He puts it to the same hash function, he gets a different result. So we have this consistency, irreversibility, unpredictability. Yeah, great. No questions yet. So to summarize, we've got symmetric encryption. We don't use that in Bitcoin. That's my sister passing notes. We've got asymmetric encryption, not used in Bitcoin. That's Glenn Greenwald and Edward Snowden sending messages about the government to each other. We've got asymmetric authentication that is used in Bitcoin. That is where you have a public key and a message, and other people can verify that you signed the message. And we have hash functions where you take any amount of data and distill it down to a fingerprint. So in Bitcoin, we have these principles. A user can prove that they know a private key connected with a public key, and we have a way of irreversibly, unpredictably, but deterministically compressing data. These are our 2 important crypto principles for Bitcoin. No questions yet. So now let's go back to that bank. And Crystal's going to be happy because we're going to start to use some encryption. Or actually, what we're going to do is throw away the password entirely. We won't have to worry about it. It's going to be great. So now our bank database looks like this: 2 columns, a public key and a balance. No username, no password. When a transaction comes in, it might have these fields. It has the sender's public key, the recipient's public key, the amount, and a cryptographic signature. And we do basically the same 2 checks we did before. Is the signature valid? So we take the public key, the message, which I'm waving my hand at that for now, and the signature, make sure that it's cryptographically valid. And then we look at the balance. Does the user with this public key 2BA03DD have enough to spend to? Yes, they do. The database mutation looks like I've illustrated it below. The account with public key 02BA03DD goes from 15 to 13, and the recipient 1100EAEA goes from 100 to 102. All right, it's a lot like the first bank that we looked at, but now we're using signatures. What happens when we send to a public key which isn't present, as we are not checking for a valid public key? Okay, that's a great question. We're not covering that in my extremely simple crypto bank, but the answer to that, let's make up the answer. I'll say that the answer is that if you're sending to a public key which isn't in my database yet, I add it. I add that public key to the database and give it a brand new balance of whatever you just sent. So that's another kind of interesting thing about this model, is that users don't need to create accounts to get involved. And people can send money to any public key. They can even send money to public keys where there are no private keys, and that money is just unspendable forever. Interesting. Okay. So we've got the account-based model, which I've just described. It's actually used in some cryptocurrencies like Ethereum, but not by Bitcoin. We're getting closer to how Bitcoin works, but So far, we're talking about the account model. Private keys are kept secret by individual users. Bart, Homer, Lisa, Nelson, they've each got their own keys, green, yellow, blue, red. And they can verify, if they all get the same transactions, they can all basically maintain the same database, this table. They can all if they all get the same amount of transactions, they can maintain this record of public keys and balances if they all do the verification correctly. Okay, that's called burning of Bitcoin. Correct. That's the term. You could say Bitcoin is being burnt if you set it to an unspendable address, especially if it's provably unspendable. Okay, so here's our first interesting pivot. This is where things start to get more interesting about Bitcoin versus the account model. The account model is sort of represented here on the left. This is something I'm sure everybody is familiar with. Username, password, that's how you get access to your account. And that's how the account model works in these slides that I've been showing you so far. Bitcoin does not work like that. Bitcoin works on something called the coin model, or we'll call it the UTXO model. And instead of tracking people's accounts by their identity and their balance, what we track instead are units of money, because Bitcoin is designed to be more like cash. So instead of the model on the left, where we have usernames and passwords, what we're going to do is more like this model on the right, where we keep track of bits of money. Each of these coins, I have a picture of bills here, but bills, coins, bear with me. Each of these coins has certain properties. They have a value. I've got a 1, a 5, and a 10, and they have an identifier. The identifier on this $1 note is B238258663D. And notice that they're separate, and Bitcoin database is going to track things like this. So here's what the Bitcoin database actually kind of looks like. Instead of accounts, we don't have public keys and accounts. What we have is identifiers for these chunks of value. They have an identifier, a value, and something called a challenge. The challenges that I've listed here are all the same for simplicity. We're going to get more into that later. But this is how the Bitcoin database works. We keep track of all these coins. They have identifiers, values, and a challenge. The first challenge I have here is sign this identifier with public key 02BA03DD. And as you know from what we've already said about signatures and transactions and stuff, you can probably already see where we're going to go with this. So here's an example of a Bitcoin transaction using this kind of metaphor. It's an object. It has two arrays. The first array destroys coins. The second array creates coins, or you can think about them as spending. It's better to think about it as destroying and creating, because that's how it's going to really apply to the database. So this transaction is going to destroy the coin 62A03142. You can see that's, here's the third one down on our table. It's worth 19. And the response to the challenge is the signature. So the signature is going to have, the response is going to have to satisfy the challenge. The challenge says sign this identifier with this public key, and we're going to respond to that with a signature. And then we have a second array, create coins. We're going to create two new coins that will be added to this table. These two coins have values of 10 and 9 respectively, and they have challenges of signing with two different public keys. So how do we verify this transaction? First thing we need to make sure is that the coin that you want to destroy exists. If it doesn't exist in the table, you are forging money, and I don't like you. You're mean. The next thing we want to do is verify the cryptographic signature. We want to make sure that the response matches the challenge. So we do our asymmetric authentication check and make sure that the signature was actually created by the owner of the private key that corresponds to the public key. That's got to be valid. And then we also need to make sure that this transaction is not creating money that didn't exist before. So the coin that's being destroyed is worth 19. The two coins that are being created are worth 10 and 9. That is satisfied, less than or equal to. So this is a valid transaction. And the database is mutated by that transaction in this way. We delete the coin 62A03142, wipe it out of the database. It is spent, it's gone, it does not exist anymore. And we add these two new coins, one worth 10, one worth 9. They have the respective challenges according to the as instructions from the transaction. So we've destroyed a coin and added two more coins. No questions yet. That's good. So I'm gonna tie this up a little bit and kind of bring it back to how it actually works in Bitcoin. Let's say Bart wants to pay Lisa 10 BTC. He must be buying a house or something. Bart has a 19 BTC coin in his wallet. Bart's transaction destroys the 19 BTC coin and creates two new coins. One coin is worth 10 and goes to Lisa's public key, which he gets somehow. They live in the same house. Maybe she just gave it to him. And then the second coin is worth 9 BTC, and that goes back to Bart's own public key. That's called a change address. If you go to Starbucks, you buy a $5 coffee for $10, you're going to get your coffee plus $5 back. That $5 goes back in your wallet. Same thing. We got change here. But notice that like that you're in that Starbucks metaphor, you're destroying the $10 and you're getting a $5 back. And then the challenge. So here, all the challenges I've shown you so far are just sign a message with a public key. This is where things get really, really interesting in Bitcoin and where a lot of the new soft fork proposals come from. The challenge can be extremely flexible. You could even describe it as a smart contract, although since the invention of Ethereum, the buzzword smart contract has sort of a different meaning. But these challenges can enable certain things like multi-signature, where, for example, say Adi and I have a company together and we want some money that requires both of our approval. I have a private key, he has a private key. We can create a series of transactions, or basically we can create a wallet where the money can only be spent if he and I both sign the same transaction. If he tries to take all the money out of the company without my signature, it just won't work. Time locks. You can create transactions where the new coins cannot be spent until a certain amount of time has passed. And this kind of thing is those two primitives build up towards a Lightning Network, which I really hope you guys learn more about this summer. But the flexibility of these coin challenges can be the basis for all kinds of interesting applications on top. So I will give you the actual Bitcoin terms that you and your mentors and that you'll be using in your Bitcoin career from now on. When I say destroy coins, those are actually inputs to the transaction. When I say create coins, those are the outputs. So transactions don't actually destroy and create coins. We say they have inputs and outputs. Coins mean UTXO. It stands for unspent transaction output. The database you can refer to as the UTXO set. This is a picture of the UTXO set in my Bitcoin metaphor. It's the list of unspent transaction outputs that exist. The challenge is called the output script. In the code in Bitcoin Core, you'll see it referred to as the script pub key. The response is called a script sig or a witness. More on that later. And the coin identifier is called the transaction hash or the TXID, the transaction ID, as well as the transaction output index. And that'll be a little bit more clear as we go forward. So, these words on the left here are the ones that I used in the slides. The ones on the right are the actual Bitcoin terms. Okay, so I'm going to show you some actual Bitcoin stuff now. Now that you understand the metaphors, this is what an actual Bitcoin transaction looks like in JSON format. Obviously, on the internet, the message is serialized and compressed. We don't need a lot of this junk, but we can see what we've got here. We've got a TXID. That's basically the hash of the transaction. The version, transactions have a version number. The lock time explains when the transaction is allowed to be mined. We can talk about that later. Then we have these two arrays, like I promised you. There's a V in and a V out. The transaction inputs, the transaction outputs, otherwise known as the coins being destroyed and the coins being created. If you look at so this transaction in the screenshot here has one input, two outputs. The first input, let's see, has a value of, these are in Satoshis. So you got to imagine a decimal point, 8 digits in there. I'm not going to try to do this in my head in front of everybody. This is like 135 Bitcoin or something in the input. And you can see that the script pub key, the challenge, is op dupe op hash 160 op push bytes. And we can talk, and then there's a public key and then equal verify and op check sig. It's a bit of an old fashioned transaction, but what this challenge is doing is saying, provide me with a public key that when hashed equals this hash, and then use that public key to verify a signature. The actual signature is here in this script sig. That's the actual signature, and the pub key hash is there where it says script pub key. So I'm getting a little confusing here, and that's the input of the coin that's being destroyed with a signature. Then the V out are the new coins that we're creating. It looks a little bit simpler. They have values. The first value is 5 million Satoshis, and the other coin is 135 million Satoshis or something. And they have their own challenges, op hash 160, push bytes 20, and then something, and then an op equal. And you might notice that these two outputs actually have different challenges, very different challenges. The first one is just hash 160, push bytes 20, a hash, and then op equal. The second one is op dupe, op hash 160, op push bytes 20, some kind of hash equal check sig. These are two different types of challenges. In fact, there are two different types of Yeah, two different types of outputs. So right away, you're seeing that one transaction can be very flexible. You're creating two different types of coins that individually are going to be spent in two different ways. Let me answer this question. If the UTXO set is the database in the metaphor, what would be the place of the blockchain in that metaphor? Okay, that's a really good question. And I don't have a slide for this, but let's talk about it. So this is great. Actually, when I give talks about Bitcoin, I will ask the audience, I'll say, so everybody basically knows, right? What is the most important data structure in Bitcoin? What is the data structure that actually is the most important thing to do Bitcoin? What is it called? Somebody type it in the chat. Somebody type in the chat. What is it? I ask a room full of people, what is the most important data structure in Bitcoin? And Merkle tree. Okay, that's actually good. Blockchain. There we go. Blockchain is the answer that I expect. The truth is, that's wrong. UTXO set. Thank you. Andreas got it right. Pedro got it right. The UTXO set is actually the most important data set. This is the list of real coins, of coins that exist. And the blockchain, you can think about it as the data you need to create the UTXO set. The blockchain is basically your input, and the UTXO set is what you really need. So that means that, do you really need the blockchain? Well, actually, you don't need to keep the entire blockchain on your disk your entire life. And that is why we have something called pruning. So if you want to, if you have a 1 terabyte hard drive, you can download the entire Bitcoin blockchain with its, where are we at? 100,000 blocks? I don't even know. And store those on your disk forever. And you will have a copy of every transaction made for the last 11 years. But as you're downloading those blocks, you're creating the UTXO set, and doing these database mutations that I've described, taking each transaction, applying it to the UTXO set. And in the end, you have a complete UTXO set. You don't need that 500 gigabytes of blockchain data anymore. So what a pruning node does for the user is it starts deleting blocks. It starts deleting blocks that are at least 2 days old, and that's configurable depending on your software. So with a prune node, you can actually run Bitcoin your entire life and never actually use more than 2 gigabytes on disk, or maybe it's even less than that. So I hope that that answers your question, Satonomi. If the UTXO set is a database, what is the place of the blockchain? Shortest answer is the blockchain is the input to your computer program that maintains the UTXO set, which is actually the important part. Okay, and so we talked about how this transaction actually works. I added 2 new slides to my talk this year. Great, you're welcome. This is the list of the Bitcoin opcodes. So the challenges aren't just sign this with a pub key. As I mentioned, you can do lock times, you can do multi-sig, you can call it a smart contract if you want to use the old school definition. The Bitcoin, those challenges are written in a language called script. It's a programming language. And this is what it looks like. These are the commands. The ones in purple have actually been deprecated. They were determined to be potentially antagonistic to the network, or like denial of servicey, or not unstable. I think they were actually disabled by Satoshi very long time ago, but they're still defined. And yeah, more on that later. And then you can see on the right, there's actually some no-op codes. These are kind of interesting. That is a very nice present from Satoshi to leave us opcodes that do nothing, because we can define them in the future. In fact, 2 of them have already been defined: check lock time verify and check sequence verify. These are opcodes that Satoshi did not invent. These are opcodes that have replaced no-op2 and no-op3, which is kind of interesting. And we can do those with soft forks, so we can expand the Bitcoin programming language. You guys might have heard of opcheck template verify, which is a proposal by Jeremy Rubin to add a new opcode to the Bitcoin script. There's a lot of technical debate about that, a lot of alternatives. This is what they're talking about, is adding commands to the Bitcoin script language. I also have one in green, opcheck sig add. This is a new one that is only valid on the network starting in November, when Taproot was activated. BIPs 340, 341, and 342. Checksig add is defined in BIP 342. It's an opcode that is only allowed in Taproot scripts. Yeah, so Yeah, lots of cool stuff we can do there. Another thing I wanted to throw in here is the concept of signature hashes. So up till now, I've been saying sign the transaction, public key, private key, signature. Well, what is the actual message when you're signing a transaction? Like, oh, wait, what are the actual bytes that you're signing? You can look on the Bitcoin wiki and see a great graphic on what op checksig actually does to the transaction. Obviously, you can't sign your own signature. So some parts of the transaction need to be kind of ignored for a little while, where you put a placeholder there and come up with some sort of serialized chunk of data, hash that, and then sign that hash. And it turns out that we are flexible in this area also. You can tell the verifier which parts of the transaction you are actually committing to with your signature. And these are some of the examples. So this is a Bitcoin transaction I screenshotted from blockchain.info. And this is a really colorful example. Most transactions you will sign with your wallet use SIGHASH all. That's the red box. It commits to all the inputs and all the outputs. So all the input data and output data is serialized, hashed, signed, that's SIGHASH all. But there are these other options. There's SIGHASH none, where you only sign the inputs and none of the outputs. Oh, that's interesting. So that means if I have a 19 BTC coin, I can create kind of a part of a transaction, an incomplete transaction, where I sign that input, but I don't commit to any outputs. Well, that means that anybody can add an output to that transaction, or we can have multiple versions of the same transaction trying to spend that same output to multiple people. There are some reasons why you would want to do that. Any prev out is this proposed opcode that is not merged yet into Bitcoin, where it just signs the outputs and then you can add different inputs to it. Anyone can pay is similar to that, where you still commit to one of the inputs, but not the other. So if this transaction was, if the first input was signed, anyone can pay, anyone else could add a second input. And this is interesting for projects, let's say crowdfunding. So let's say I say, hey, everybody, if I raise enough money, I will do this thing. So I can create a transaction where there's an output that sends 100 Bitcoin to me. That transaction is not valid, remember, until the input value is greater than the output value. So I can broadcast it. I can put it on Twitter and say, here's half of a transaction that pays me 100 Bitcoin, and I just need somebody to fund it. And you can sign it this way, and even multiple people can fund the same transaction. You can keep passing it around Twitter until enough people have added inputs that the input value is greater than the output, and now it's valid and we can broadcast it. That concept is actually called Lighthouse, and it was invented by Mike Hearn back in 2005 or 6 or something. The idea was to create a decentralized Bitcoin Core development fund where people would basically create proposals like I've just described and try to get funding from people, even anonymously, by creating a transaction that the community could fill with value. Why wasn't the TapScript added in one of the no opcodes? So that's actually a good question, and you should look at BIP 342 to sort of understand that. The reason, let's see, I think it's because they the way they wanted to do this soft fork, they could have added checksig add in as one of the no ops, but they decided to keep it isolated to TapScript. And I think that is probably because of the you guess a good question. I'm going to guess it's because of how they wanted the soft fork mechanism to work. There's just one basically soft fork that adds all these rules. And if you do not validate the Taproot soft fork, you basically ignore all Taproot transactions. If checksig add was inserted as a no-op, then that would kind of be a different soft fork. It would be a separate soft fork because that would be a separate set of rules. Nodes would see transactions that were not Taproot transactions, but still had this new opcode. And so they just wanted it all to be in one thing. You either do Taproot or you don't. And Taproot is BIP 340, 341, and 342 all together. One soft fork, all these new rules. So TapScript is only valid in Taproot. I'm sorry, checksig add is only valid in Taproot transactions. And I didn't colorize it on this slide, but actually checksig and check multisig, where are you guys? You're in here somewhere, are actually not valid in Taproot. We really want you to use checksig add, or multisig has been removed, and checksig add is like the new thing. I'm sorry that was confusing. I hope that answered your question, Panchu. All right, so we got inputs and outputs, we got script opcodes, we got these SIG hash flags, we can do all kinds of cool stuff with transactions. One new question here from Anmol: if anyone can add an input and the input is not part of the signature and anyone can pay, then how will we verify the inputs? And the input is not part of the signature and anyone can pay. How will we verify the inputs? Okay, so this is getting a little advanced, but let's say the transaction on the screen right now is it will follow the anyone can pay balloon. So I create a transaction with where I'm spending 8 BTC and I want to send it to these 3 outputs. And that input has my signature spending my 8 BTC with an anyone can pay signature. That means that anybody else can add that second input, or they can add any input they want, really. And then how will that person sign it? Probably with SIG hash all, for example, and then you'll have a valid transaction. So if anybody can add an input and the input is not part of the signature, how we verify the inputs? I guess it's because like each input is basically verified individually. So when you look at input 0 here, you'll look at it and you'll see the SIG hash flag anyone can pay. That only applies to that input. So when everybody's full node around the world is verifying this transaction, they look at the input, they create a message that is composed of that input and all the outputs, hash it, check the signature for input 0, that's valid. Now we move on. Look at input number 1. Maybe this one is signed with SIG hash all. We reserialize the transaction, come up with a completely different message that commits to all the inputs and all the outputs. Hash that, check that signature in input 1. Obviously, both of those signatures have to be valid for the whole transaction to be valid, to go in a block to make the block valid. Got it. Great. Okay. So we're done, right? We use asymmetric authentication cryptography to maintain a database, spendable coins, that's called the UTXO set, that anyone can access. If a transaction's signature is valid and it passes all the rules, we update our database accordingly. Transactions go to all Bitcoin servers on the internet. So everybody's Bitcoin server is in sync, right? Bart, Homer, Lisa, Nelson, they all get the same transactions. They all apply those transactions to their own databases. Everybody has the same database, right? I'm going to take a sip of tea while somebody tells me what we're missing. Anybody, what's missing from this? Something, are we done, or transaction order? Okay. Miners verifying the transactions. Those are kind of consensus and transaction approval. Okay, these are pretty close. I'd say Ayush with transaction order is probably the closest to the answer I'm looking for. Who will check transaction signature is valid. So I'll address these. I'll address these. I hope that you guys are so good. Putting it on the blockchain, P2P network, check the transaction signature is valid, consensus transaction approval, miners verifying the transactions. So all these other answers are close, but they're already, Imol has got the correct response here. Everybody maintains a blockchain. So in my picture, Homer, Bart, Lisa, and Nelson are all verifying all transactions. They're making sure that all the transactions are valid. So are the miners. But everybody is verifying that every transaction is valid. And ideally, they come to consensus is the right answer. And this is where we get to Satoshi Nakamoto's actual invention. Everything up till now has always been around. And now we're going to see what Satoshi did to actually create Bitcoin. Here's the scenario. Since all we're doing is verifying signatures on transactions, what if Nelson, being the bully in the show, created 2 transactions that both spent the same coin? So let's say Nelson owns coin A with his private key, and he makes one completely valid transaction with a totally valid cryptographic signature that destroys coin A and creates coin B, which goes to Bart's public key. He also creates a similar transaction that destroys the exact same coin, coin A, but instead of creating coin B, it creates coin C, creating a second transaction that goes to Lisa, and he sends these transactions to the respective parties. You can see with the colors on my diagram here, now our databases are not in sync. What has Nelson done? He's basically spent the same money twice. Imagine like going to a Starbucks, buying a coffee for $5, then going across the street and buying a sandwich with the exact same $5. Obviously, if we're creating a money system, that shouldn't be allowed, right? That'd be Nelson creating money out of thin air. We need some way to prevent Nelson from double spending. Double spend problem. You're absolutely right. And not only do we need a way to prevent him from double spending, we need a way for everybody in the network to either, not necessarily know that he's double spent, but just be able to verify which of these transactions happen first. That's the rule here. We could have come up with any number of rules. We could have given Lisa priority over Bart and somehow made that part of the system. How Bitcoin works is whichever transaction happened first is the true transaction. Okay, so how are we going to fix this? I'm going to refer you back to my definition of hash functions from earlier, and in particular, the example of SHA-256. Secure hash algorithm 256 means it's 256 bits long, the output. No matter what the input data, the output will always be 32 bytes. You can hash one letter, you get a 32-byte output. You can hash all of Wikipedia, you'll get a 32-byte output. The output is indistinguishable from random noise. That's self-explanatory. The same input always produces the same output. Recall the little chemistry set thing. If I take the SHA-256 of the letter B and you take the SHA-256 of the letter B, we're going to get the exact same output. The function cannot be reversed. If I give you a hash, if I give you a little distilled drop of chemicals, you have no idea what went in, what the input to the function was to create that hash. But if I give you the input, you can verify it because the hash function's output is always the same. So here's an example. These are the actual SHA-256 hash outputs of these 1, 2, 3, 4, 5, 6, 7 strings. If you take the hash of the letter capital B, you're going to get this 32-byte hash. If you hash BI, you get this one, BIT, blah, blah, blah. And as you spell the word Bitcoin into the hash function, the output is completely different. All 32 bytes are completely different just by adding an extra byte to the input. And actually, if we even just changed one bit in the input, we would get a completely different output. That property is what makes SHA-256 secure. And by the way, if anybody was ever able to break that property, basically like they have with SHA-1, that hash function would be unusable, it'd be cryptographically insecure, and nobody would be able to use it again. So hopefully SHA-256 is enough to last us a very long time, and not just because of Bitcoin, but because of basically everything on the internet. It really likes this hash function. One thing you might notice about this, though, is if you look at row 2 and the second from the bottom, the hash of BI starts with the byte 6B, and the hash of BITCOI also starts with the byte 6B. That's kind of interesting, right? Now, the hashes are, if you look at all 32 bytes, they're wildly different, completely different. But it is interesting to note that every now and then, the first byte of two hashes is the same. That's interesting. Let's talk about that. If I give you this hash, can you tell me what the input is? You can. It will probably take you 2 to the 256 random tries to find it. You can basically, it's basically like flipping 256 coins and trying to get the exact same sequence. It's going to take you a really long time, basically probably more time and energy than is available to you in the entire universe. So you'll probably never be able to find the actual input for this hash. Well, what if I asked you just to find the input for just the first byte? So find the input to a SHA-256 function where the first byte equals DA. If you guys, somebody could probably do this in the next 5 minutes, because the first byte is only 8 bits, which means it'll probably only take you around 256 random tries, take 256, random data inputs to SHA-256, and probably at least one of those will have a hash output where the first byte is DA. So now that's very easy, right? This basically impossible. This probably pretty easy. You could do this instantly. You could do this instantly on your cell phone. Imagine flipping a coin and getting tails 8 times in a row. That's practical. That would probably only take you a couple hundred attempts, and then you flip your 8 coins and they'd all be tails. So now let's bring this together here. This is an actual Bitcoin block hash from height 666208. You can tell I made this slide last year. It starts with 76 bits of 0. And we're looking at it in hexadecimal here, so you're not going to see 76 zeros. But if we were looking at it in binary, you would. This hash starts with 76 zeros. So does that mean somebody actually tried 2 to the 76 random input values to come up with this hash? The answer is basically yeah, and not just somebody, but everybody on Earth, all the miners on Earth trying all simultaneously. So again, sorry, I didn't update this slide for 2022, but when I wrote this slide, the current Bitcoin network hash rate is this incredible number. I don't even know, is that 147 exahash or petahash? Probably exahash. Huge, crazy number per second. And even at that insanely high hash rate, it still takes 10 minutes for some computer somewhere on Earth to find the input to the SHA-256 hash function, whose output starts with 76 zeros. You should feel that in your gut. Like when I think about it, it's like, that's like so cool. This is called Hashcash. This is the definition of proof of work right here. It is really, really, really hard to find input to a hash function where the output starts with 76 zeros. And even with the world of incentivized miners trying, at this incredibly high rate, 147 hashes per second, it still takes 10 minutes for somebody to actually accomplish this. That's so hard to do that Bitcoin is secure. That's the assumption. This is the thing that Satoshi Nakamoto put together and invented. This is where the security model of Bitcoin comes from. And I'm going to show you how we can use this to protect Bart and Lisa from Nelson's little double spend attack. But is there any questions about this, the essence of proof of work here? We're trying to find the input to a hash function that creates a partial collision. Obviously, we can't create the entire 256-bit hash, but any hash that starts with a certain value is acceptable. We know it's very hard to do. We know basically exactly how long it should take somebody to do that. All right, great. You guys are all super smart. Proof of work. So now we're going to start talking about blocks, and then we'll be able to prove which of Nelson's transactions is valid. So now we're talking about blocks. I've got 3 blocks on the screen here. Block 0, which is our Genesis block, block 1, and block 2. And a block is a list of transactions combined with the hash of the previous block and a nonce. So block 0 starts with a null previous block. There is no previous block. It's block 0. It's a Genesis block. It's a starting point. It's the only block basically that's allowed to not have a previous block, because that wouldn't make any sense. Then we have a bunch of transactions, and then we have a nonce, which I'll explain in a second. Block 1, so the hash of block 0 is 00B1CC. That's if you take the SHA-256 of the entire block. With those transactions and the nonce, you get 00B1CC. We take that hash and put it at the top of block 1, and then list more transactions and add another nonce. And then we take the hash of that block 1, which is 000AC2, and we put that hash at the top of block 2 and add some more transactions and a nonce. So in this way, each new block points to the previous block by including the hash of that previous block in each new block. And you'll notice that these arrows point from right to left. And if you go look at Satoshi's white paper, he actually did it wrong. It's like the guy doesn't understand Bitcoin at all. Satoshi's white paper, the blocks go from left to right. Haha, what a dope. He did it wrong. It's one of the many errors that he left us in the white paper. But when you explain this to your friends, when you explain this to your 50-year-old cousin over dinner, you're going to tell her that the arrows go this way. Okay. So the nonce is where things get interesting. It's where we actually talk about mining, because the hash of the previous block is fixed, right? We can't change that. That's what makes this into a chain. Then we add some transactions. We can assume that those are basically fixed. We take transactions from the network, add them to our block, and then we take a hash. And then we need to be able to try different inputs into the hash function, and that's where the nonce comes in. So we take the previous block hash, our transactions, and a nonce. Nonce is a number used once. We'll start with 0. We add a 0 to this list of transactions, hash it, and we get a hash that does not meet our target. Okay, now we try 1, hash it again, doesn't meet our target. No, now we try 2, hash again, doesn't meet our target, and so forth. This is where we get the concept of hash rate. This is where we get things like ASICs. This is what mining machines are doing, is they're taking the block template, which is the previous block's hash, a list of transactions, and then we keep adding a nonce to it, different nonces as fast as we can, hash, 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 until we find a hash that starts with 76 zeros. Okay, metaphor in my little metaphor here. Valid blocks are also allowed to contain a special transaction called the Coinbase transaction that creates brand new coins. This is the only time this is ever allowed. This is how miners generate money. So in my blocks here, block 0, 1, and 2, you could say transaction A, D, and G. The first transaction in each block do not destroy coins. They only create coins, and those coins go to the miner's address. This is how miners get rewarded for their proof of work. They generate new coins. All coins in the Bitcoin blockchain are created by this mechanism, and that's how it's done. Find the right nonce. Go. Any questions yet? We got proof of work now. We got blocks. We got a blockchain. We actually have a blockchain. Here we are. We're 53 minutes into the talk. We are actually having a blockchain on screen. We're mining. Everything looks good. Next concept is something called chain work. And this is actually something that another thing that Satoshi Nakamoto got wrong in his white paper. So after today's talk, everyone's going to know more about Bitcoin than Satoshi Nakamoto. Satoshi's mistake was he talked about the longest chain in the white paper. So if you have, 100 blocks versus a 50 block chain, the 100 block chain would be the truth. Well, that's not necessarily the most secure. So in Bitcoin, we have this concept called chain work, and you can think of chain work as the total number of 0 bits in the hash of every block on the blockchain. So let's go through these 3 blocks I have here, block 1, 2, and 3. The hash of block 1 is 0f11cc. That is a hash that starts with 4 bits, right? 0f is 00001111. So we can say that block 1 has 4 bits of chain work. And we know, using the flip a penny example, that it would take 4 penny flips, 2 to the 4th, to find that block. Not a whole lot of work, just 4 whatever hashes. Now block 2, the hash of block 2 is 00FFC2. This hash starts with 8 zeros, right? The first byte 00 is 8 0 bits in a row. We add that together. So at block 2, we now have a chain work of 12. At block 3, the hash of block 3 is, let's say it's 0000B4. Actually, this was true when you wrote the white paper. He changed afterwards. Thank you, Davidson. Davidson is correct. The actual Bitcoin, original Bitcoin code base did actually follow the longest chain, which they realized later was insecure, and they changed it to this chain work model. So Davidson's right. If nobody corrected Satoshi's mistake, Bitcoin could be much easier to attack. Thank you. And how does 10-minute timestamp stay consistent if the proof of work aspect is by chance? How do miners solve the problem in a consistent time frame? Great question, Autumn. I will explain that. Let's see. Do I get that in the next? No, I'll explain that as soon as I'm done with this slide. So does everybody understand chain work? As we add blocks to the chain, the total chain work goes up. And you can imagine, and because the hashes of this chain, so you can imagine if block 2 had a different hash and block 3 had a different hash, by the time we got to block 3, we might have a total chain work that's less than 28. And we know, because of how proof of work works, that the chain with the most zeros, basically total, was harder to find, was more expensive, consumed more electricity, and is therefore more secure. Okay, hopefully everybody understands that, and I'll now answer Autumn's question. So the one thing that I leave out of this talk is something called the difficulty adjustment, because it's not really a basic concept. But since you guys are all super smart, I wouldn't explain this to my cousin over dinner, but maybe if you guys are talking to another computer science major, someone who already understands Bitcoin, you could talk about the difficulty adjustment. So I'm going to step back a little bit. Whoa, not forward. I'm giving my slides away. Okay, so this was the hash of block 666208 from almost exactly a year ago, and it started with 76 bits. How do we decide that 76 bits is the target? It's another very clever invention by Satoshi Nakamoto. It turns out that there is a consensus rule in the Bitcoin network that decides what the target value is going to be, how many 0 bits you need, or more literally correct, if we interpret this hash as a 256-bit integer, we need to find another integer that is less than this target. I'm not sure if I said that correctly. We need to find a hash that is less than the target, if you consider the target and the hash both as 32-byte integers, 256-bit integers. So we have this thing called the difficulty adjustment algorithm. And here's how it works. Every time you make a block, one thing I left out of this illustration is that each block also has a timestamp. It's a UTC, probably 32-bit timestamp, just like you've seen all over computers. The timestamp has some rules. The timestamp, so when you receive a block, how do I know that my clock is in sync with everybody else's clock on the network? And that is actually a problem that Bitcoin has to solve. We need to, every time we connect to a peer, I'm like, hey, what time do you think it is? And the other peer is like, I think it's about, 1358 UTC. And I'm like, okay, well, he's maybe 1 or 2 seconds ahead of me, or 1 or 2 minutes. So I'll make a note of that. We try to keep all the nodes basically in sync time-wise, wall clock time-wise. Okay, here comes a block. It has a timestamp in it. Some of the protocol rules involve checking that timestamp. For example, the timestamp cannot be more than 2 hours in the future. So right now, and that's a rule. You can find it in Bitcoin Core. You can find it in the code base. So right now it's 1358 UTC. If a block came in where the timestamp was 1600 hours, I would reject that as being an invalid block. You've just wasted your proof of work. I'm not going to add that block to my chain. No, thank you. And similarly, there's the timestamp can't be too far in the past. It uses something called median time passed. It's a little bit more complicated, but let me just say that the timestamps in blocks need to be within, let's say, a 3-hour window. So they can be anywhere in there. They're still valid, even if the timestamp is an hour ago or almost 2 hours into the future. That is still a valid block. And one of the most frequently asked questions about Bitcoin when people start looking at the blocks is, how come block 1 has a timestamp after block 2? This will happen because there is a 3-hour window that timestamps are all still valid. So sometimes the timestamps in blocks will actually get mixed up, and it's still valid. Okay, so every block has a timestamp in it now. So here's what we do. We have this concept that we want new blocks every 10 minutes. And we have this target difficulty that's back here. So we have this thing called the difficulty adjustment algorithm. And here's exactly how it works. Every 2016 blocks, your Bitcoin node will look at the last 2000, will look at the block 2016 blocks ago and make sure that the timestamp in that block is exactly 2016 blocks times 10 minutes ago. So we look at how long it took the network to produce the last 2016 blocks, and we divide it by 10 minutes, which is our goal, which is a constant. It's a protocol rule that's in stone forever, 10-minute blocks. And so we look at how the network has produced the last 2016 blocks. Maybe it's too fast. Maybe it's too slow. And if it's too fast, we change, whether it's too fast or too slow, we change the target for the next 2016 blocks. So bringing it all the way back down to Autumn's question, how does the 10 minutes timestamp stay consistent? This is your answer. Every 2016 blocks, every Bitcoin full node does a quick calculation to determine how fast the network in total is producing blocks. And then we make the mining target either easier or harder based on that calculation to try to make the next 2016 blocks hit that 10-minute target. Autumn, did I answer your question?
Yes, thank you.
Okay, great. Yusuf asks, can multi-sig wallets be controlled by a person if the other party is not available or the wallet is gone? Interesting. Let me see what Pranchu's question is before we move on to that. The difficulty of mining changes every 2016 block to roughly every 2 weeks and tries to keep up with the average block mine time. So block time is 12 minutes. Okay, great. Pranchu has added an answer to Autumn's question. Yusuf's question about multi-sig. So this goes back to scripting and wallets. If the other party is not available or the wallet is gone. So I actually don't really take a deep dive into Bitcoin script in this talk, but I did kind of hint that there's this whole programming language. And if you look at the scripts in this transaction, you can basically see 3 different types of scripts. I don't have a multi-sig here, but you can come up with whatever you want. You can make a Bitcoin script where either I can spend it, or Jessica can spend it, or Autumn can spend it, or Adi can spend it. All 4 of us. Maybe it only takes 1 signature. We can call that a 1 of 4. Maybe it's a family, or maybe it's you and your partner, or you and your wife or your husband, and you have a 1 of 2 wallet where you can either of you can spend the money. You don't need to share private keys. I can spend the money with my private key. My wife can spend the money with her private key. So the question that Yusuf asked, it depends on what you want to do. You might have a company with a board of 10 people, and you need all 10 people to sign that transaction for it to be valid. In that case, if one of those 10 people is not available, you cannot spend that money. So what I would recommend for your company, if there's somebody who might not be available, is maybe you make your wallet policy 8 of 10. 5 of 10, 7 of 10. That way, if 1, 2, or 3 people is not available, the other 7 people can still sign. So to answer your question, Yusuf, it depends on what you want to do with your wallet. You can program it any way you want. Schlock asks, why can't we reduce the time? Isn't faster transaction a better choice? Okay. This is a really good question. I think that was chosen by Satoshi, just like 21 million BTC. Panchu is basically correct. Satoshi had to make a lot of guesses about what would be best. And you can find a debate about this on Reddit or on Stack Exchange about whether the 10-minute time is good or bad. And I know a lot of you are probably familiar with other blockchains like Ethereum, where they have a block time that is, I think it's like 10 or 11 seconds. And some other blockchains have difficulty adjustment algorithms that change every block. For example, I think Bitcoin Cash is like this. Instead of waiting every 2016 blocks to recalculate the mining target, it'll happen every block. And there's different design reasons for that. One thing that I heard about the 10-minute time is that, and this is something I heard from Mike Hearn on Reddit probably 10 years ago, is that Satoshi did some estimation and assumed that it might take 1 full minute for a brand new Bitcoin block to completely propagate to every node around the world. And if you're a miner in San Francisco, California, and you're trying to find the next block, and meanwhile somebody in China finds that block and they broadcast it, while that new block is being propagated across the network, that miner in San Francisco, he doesn't know about it yet. He's wasting energy now. He's wasting mining effort because he's still trying to mine a block that somebody else has already found. Eventually, that block will get to him or her in San Francisco, and they'll be like, oh, I just wasted, I need to stop and start mining the next block. So in that sense, you could look at it that some of that energy was wasted while the first block was being propagated. So if you like, one theory about the 10-minute number is that Satoshi just decided that since it would take 1 minute to propagate blocks across the network, 10% is an acceptable amount of mining energy to waste. Yeah, that's, maybe that's one explanation. Another thing was he might not have considered things about why Ethereum is so fast. I would also throw in here that light clients, SPV or neutrino clients, which I don't really talk about in this lecture, it's less work for them to do. If you're only looking at block headers, for example, it's a lot easier to verify 144 block headers per day on the Bitcoin network than say an Ethereum light client, which would have to verify 1,000 times more than that or something. So it makes light clients easier. And then also we have the Lightning Network for instant transactions. Bitcoin makes a great anchor for these off-chain protocols, which you're going to learn about more this summer. And so it's okay for the blockchain to be slow. It really is. We have other ways to make transactions fast. So Schlock, I hope that was an okay answer to your question. What I'd love for you to do is to go down this rabbit hole, and then you come back and tell me later why you think Satoshi chose 10 minutes or whether you think that's a good idea or a bad idea. What happens when 2 parties mine a block at the same time, Ayush? Great question. Let's talk about that basically right now. So we've talked about chain work. Okay, so we're gonna, great, thank you, Schlock. I really am interested to hear what you uncovered there. Okay, so what is the truth? We're back to this. We got Nelson. He has signed 2 transactions that according to the theory of money, should not happen at the same time. One of these is true and the other is false. So what we, strongest chain will be considered, chain split happens. Okay, well, chain split might not necessarily happen, but let's say that Nelson sends one transaction to the miner in China and another transaction to the miner in San Francisco, and they're both working on their block. And let's say they both find a block at the exact same time. So I have drawn that here on this chart. I've actually drawn a little bit more than that. Let's go through what we've got here. This is a split chain or a chain fork. It's actually, this is maybe something I should make explicit in this talk next year when I give it in 2023. The term blockchain is actually not a great description of the actual data structure. It is really much more tree-like. We have a genesis block, and then we try to add blocks on top. But really, the only rule is that each block points to a previous block. So as you can see from this image, this is something that happens all the time in blockchain, and it's not a chain, it's a tree. There's a root, and then there's 2 branches, right? So let's go through this. We have the first block on the left, 0F112F, with a chain work of 4. And let's say that the miner in San Francisco is on top and the miner in China is on bottom, and they both discover the next block. And the miner in San Francisco has this block, and he points to the previous block, 0FB11CC, and so does the miner in China, and they both have 2 blocks that are simultaneous. As these blocks propagate across the network, the first thing that a node will do is accept the first block. So that means if we got China and San Francisco like this, and their blocks are propagating across the globe, we will have half the Bitcoin network thinking that this top block is the tip of the chain, and the other half of the world will think that the bottom one is. And then let's say the next blocks are added by China and San Francisco, and now something interesting has happened. The miner in San Francisco has transaction I that goes to Bart, and the miner in China has transaction N, which goes to Lisa. So now not only do we have 2 chain tips, 2 branches of the same blockchain, but now they're actually really different. And it's super important, the difference. Obviously, transactions I and N can't happen in the same block. That would break Bitcoin's rules. You'd get banned from the network for trying to do that. But the top block has transaction I, the bottom block has transaction N. Maybe half the world thinks that the top row is the truth, and the bottom thinks that half the world thinks that the bottom row is. Half the world thinks Lisa has the money. The other half thinks that Bart has the money. What happens? Eventually, another block will be added to one of these 2 chains. I think I said that the miner in San Francisco is the top row. So as we tell the story from left to right, we all start with the same block. Then China and San Francisco miners come up with block number 2. Then they both come up with block number 3. But now finally, the miner in San Francisco comes up with block number 4 first. And the miner in China is still working on it. That block will propagate across the network and win. And this is something called the chain reorganization. Oops. So if you're right next to the San Francisco miner, you get these 4 blocks in the top row, 1, 2, 3, 4. That's great. You're happy. Transaction I is the truth. Nothing really interesting is happening on your node. If you're on the other half of the world, though, you get the bottom row. So you start with block 1, then you get block 2 and block 3 with transaction N. Then along comes this other block, the one on the top right. It just gets to your node somehow, and you're like, wait. This block does not connect to my chain, but it has more accumulated chain work. It has a chain work of 28, and I have a chain work of 16. I need to figure out what the history of the Bitcoin blockchain is that led to that block. That's the block I want to be on. It's got more work than my blockchain. I want to get there. And this is what a reorg is. So I don't know if you guys can see my mouse, but if you're here on the bottom right transaction with transaction N, and then you suddenly see this new chain tip with a much more chain work, you have to undo these 2 blocks. You got to take these transactions and reverse the whole process. You put the coins back into the UTXO set, and you delete other coins, and then you go to the next block and you have to undo all the transactions and put the coins back in the UTXO set until you get back to this first block on the left. And then you replay the new blockchain on the top, up, destroying coins, adding coins. This time you'll have transaction I applied to your UTXO set. Finally, you get to the block on the top right with a chain work of 28. And you're like, great. I can tell the user that we've done a chain reorganization. The database has been rewound and then replayed up the new fork. And now we're here. That's a chain reorg. And this is the most important thing. This is how we decide what the truth is. We need to find the chain with the most accumulated proof of work. And once we've done that, then we know everybody is in sync because everybody's trying to find the chain with the most accumulated proof of work. So when we get this last block on the top right, we know that transaction I is now the truth. Transaction N never happened. And you can also see why if you're selling something for a good deal of money, if you're selling a car for 10 Bitcoin, you're going to want to wait for several blocks. You're going to want to make sure the chain isn't about to get reorganized, right? And this is why, if you're sending Bitcoin to an exchange, very frequently they will wait for 2 or 3 confirmations. And also, by the way, if you are sending a different cryptocurrency to an exchange. For coins that are not as secure as Bitcoin, they will wait 10, 20, 30, 100 confirmations. And then back to the question about a faster block time. This is something interesting about Ethereum, because just because they have blocks that are faster doesn't mean that those blocks are any more secure. So in Bitcoin, Satoshi actually in the white paper recommended that everybody wait 6 confirmations, which should be about an hour, right? 10 minutes per block. 6 blocks is about an hour. He says, if you're going to sell a product to somebody, get their Bitcoin transaction, wait about an hour, make sure it has 6 confirmations, then it will probably not get reversed by a chain reorg and you can send them the goods or services. On Ethereum, you should probably also wait an hour. Now on Ethereum, that might be, I don't know what that is, 1,000 blocks, 10,000 blocks or something like that, because the blocks are so fast. You're still going to want to wait an hour. On Bitcoin, it'll be 6 blocks. On Ethereum, it might be 1,000 blocks, because you need that accumulated chain work to build up so that you're sure that there won't be a chain reorganization that will reverse your transaction. Okay, and then so now we've got this figured out. Bart wins, and this is basically the last slide. I'm going to read it together, and then we'll talk about I'll go back to the questions. The Bitcoin full node. This is the takeaway. The purpose of a Bitcoin full node is to connect to other Bitcoin full nodes on the internet and exchange messages like transactions and blocks in order to maintain for the user a database that matches the database of every other Bitcoin full node. When a user's node is in sync, they can send and receive Bitcoin transactions with confidence that the money they receive can be spent. The whole point of the Bitcoin full node. What is your job, Bitcoin full node? Bitcoin full node says, my job is to find the chain with the most accumulated work. That's what it's doing. It's connecting to peers. It's trying to get as much data as it can to figure out which blockchain has the most work, accumulated work. And that's how we know that we have a database that matches everybody else's database in the world. And we can send money. Okay, thank you very much. I just wanted to put this link up back on the screen, bitcoinstackexchange.com. A lot of your common questions are going to be answered there. And it's a great place just to hang out. And by the end of the summer, you guys should all be able to go to Bitcoin Stack Exchange and answer people's questions. It's much more fun than scrolling through Twitter. All right, so let me check the chat here. What happens when 2 parties mine a block at the same time? Covered that. Strongest chain will be considered. Chain split happens. The criteria is chain work instead of chain length. Yes, as I was corrected earlier, Satoshi's Bitcoin 0.1 only cared about the longest chain, but now we know that chain work is the better metric. And you can kind of see how that could work too. If we go back here, what you could do right now is take the Bitcoin Genesis block and never change the difficulty and just mine a million Bitcoin blocks that'll have an extremely low difficulty, and you'll get a longer chain than the Bitcoin mainnet chain. In fact, I think the Bitcoin testnet chain has something like 1 million blocks, or it's way longer than mainnet because it has a much lower, it's much easier difficulty. So that's important. Okay, the winning block records. The winning block records the transactions on the blockchain and transaction validation node. Is the number of validators fixed so as to record the transaction on the blockchain? Okay, great question. So I think this is the term validators usually comes from the proof of stake world, where blocks are approved by an exclusive set of entities called validators, and some people are allowed to be validators and some people are not. And that's handled by how much stake they have, and they have their keys out there. And we're not going to talk about proof of stake today. The number of validators in Bitcoin is not fixed. Anybody can start mining on the Bitcoin network. Anybody can do it. Obviously, nowadays it takes some special equipment, but if you were able to acquire that equipment, you could just turn it on and start creating Bitcoin blocks. Nothing can stop you. Permissionless, censorship resistant, extremely important property of the Bitcoin system. The number of validators is not fixed. Anybody can mine as long as they're willing to invest the energy that it takes to produce valid blocks. Before longest chain was considered not strongest chain. Strongest chain is the one which most, okay, that's an answer. Yes, we see your mouse. Thank you, Crystal. How often does a reorg happen on average? That's actually a good question. I should probably have the answer to that. I think it is actually very, very rare these days. There used to be, I think if you go to the BitMEX website, they will have a record of stale blocks. Basically, blocks that have forked off from the chain that were not added to by other miners. That's not necessarily a reorg. You could, it's a stale block. It's, in this slide, the bottom right is a block that is stale. It used to happen once, basically once in a while. Sometimes a Bitcoin chain split could go 2 or 3 blocks deep. But my understanding about this, and this is another thing, well, you are going to have to learn about it and come back and tell me. My understanding is that Bitcoin full node networking, block propagation, things like compact blocks and the P2P improvements are so good that blocks propagate so fast that there almost are no stale blocks anymore. And apparently when segregated witness came out, I guess it was version 18 of Bitcoin Core, stale blocks almost dropped entirely to 0 once miners started upgrading, because one of the things the Bitcoin Core developers are working on every day is getting this block propagation time down as much as possible, so we're not wasting any work. And so chain splits on Bitcoin happen very, very infrequently. On other chains with less work or worse mining propagation, you could get reorgs all the time. And by the way, on Ethereum, there are reorgs all the time. And part of that is because of that 10-second block time. There's miners all over and they're racing, and there's a block in San Francisco. And by the time, it might take 10 seconds to get to China. And by then there's another block. And so reorgs happen all the time when you get that block time shorter. Each time that the split happens, your hash power is also split. No, I'm not sure what you mean by that. I get, okay. I guess if you're like the picture that we're looking at here, if half the world thinks that this is the truth and the other half, I should say, if half the world is trying to make block number 4 on this version of the chain, the other half is trying to make block number 4 on this version of the chain, I guess you are right. You could say that the hash power is split. That's interesting. That I have to think about that. That's a good point. It might mean that in this case, it might take 20 minutes for the next block to be discovered. I don't know. But once it is, and if it propagates around the world, then everybody's working on the same chain again. That's a good question. Now you can explain to your mom how Bitcoin works. Good, go do that. Testnet has an exceptional rule. If 20 minutes pass since the last block, you can mine with difficulty 1. That's true. So testnet has, the Bitcoin testnet has an extra rule that makes it a lot easier to generate blocks because it's just a test network. So if people basically stop mining on testnet, the difficulty adjustment algorithm has an extra rule that basically allows anybody to create new blocks for free. Can you explain a bit about orphan transactions? Okay, let me see what else we got here, and I'll pick a couple questions because we're sort of getting close to time. Orphan transactions to avoid problems. I'll make the Adi will make the video available, I think, and I'll give him my slides so you guys can look at the slides. He's going to record get the incentives for miners in the main chain. What is the incentive for mining testnet blocks? Okay, what is the incentive for mining testnet blocks? Obviously there's no monetary reward because testnet coins are not worth anything. It's just for testing. And because the difficulty target is so much easier on testnet, if you're, let's say, building an ASIC, or let's say you're developing Lightning Network software or something that builds on Bitcoin and you don't want to destroy real money, that's what testnet is for. And actually, as you guys are playing with Bitcoin Core, you can do something called reg test mode, which isn't even testnet. It's a simulated testnet that only exists on your computer, and the difficulty stays at 1 forever. So if you want to see what a wallet looks like with 1,000 Bitcoin, you can spin up Bitcoin Core and reg test. It doesn't connect to any other computers on the internet, and you're the only miner, and you can generate 1,000 blocks and send huge transactions with meaningless Bitcoin. And that's how to learn, and it's how the testing suite works. And there's no incentive to do that except to test your software, test your hardware. All right, so there's a question about orphan transactions. So orphans. The word orphan means a child without a parent, right? It's kind of sad. People used to use the term orphan blocks kind of incorrectly, and there's both blocks and transactions can have orphans. So if you're a node on the network and somebody sends you a block, but you don't have and remember, blocks point to their previous block. If you get a block and you can't find the previous block, what you have is an orphan. You have a child block with no parent, and we need to handle that in a certain way. And the same thing can happen with a transaction. I guess I don't really have a great picture of a transaction chain. let's use Nelson's transaction. Let's say you receive a transaction that destroys coin A and creates coin B. Well, if you don't have coin A in your database, that's called an orphan transaction. You're getting a child transaction with no parents. You don't know what transaction it's spending. And that could either mean that the coin has already been spent in this case with Lisa and Bart. Let's say, we get to here. The reason that transaction N is invalid is because coin A doesn't exist. So we can call that an orphan transaction. So it either means that a double spend is happening or that you got transactions out of order. Let's say Nelson received coin A and then spent coin A within a minute of each other. Both of those transactions are allowed to happen in the same block, but you might get them out of order. And if you get them out of order, we'll call that an orphan. And yes, we need to handle that correctly because there could be a denial of service attack. We can't have too many orphans. We could fill up our disk or our RAM trying to save all the orphans. And so this is an implementation detail. It's Bcoin, BTCD, and Bitcoin Core might handle them all differently. You could even configure your node to reject all orphan transactions. There's not really any reason why you don't need them. It makes certain things more efficient. But if you want to protect yourself against, let's say, getting a bunch of transactions that have no parent, you could just limit it. Let's say I only allow 100 orphan transactions in memory at a given time. And when the 101st orphan transaction comes in, I delete the first one, the oldest one. So it is something that we have to manage. But orphan transactions are not allowed in blocks. Okay, that should be clear. I'll restate it though. So if coin A does not exist in the blockchain, then this transaction cannot go into a block. It is invalid. All right. Mine difficulty 1 blocks on my CPU. Very fun, informative. You're welcome. Each miner have a different mempool of transactions shared distributed. This has caused a CV past. I'm not sure what that's referring to, Davidson, but that sounds probable. Does each miner have a different mempool of transactions? This will probably be my last question I'm going to answer here. Yes, if you hear anybody talk about the mempool, you can correct them. There is no the mempool. Every single full node has its own mempool, and your mempool could be different from my mempool. The miner in San Francisco might have a different mempool, will necessarily by identity have a different mempool than the miner in China. And so that's why Nelson could try to double spend this way. And you could do it today too, actually. You could create 2 transactions today with your own Bitcoin Core wallet or with Bcoin, double spend yourself, send one to this direction on the internet, send the other to this direction, and just see which one gets mined. That'll be an interesting experiment with the same fee, So yes, mempools are different. And actually, I got one more question for you. My students have already answered this yesterday, but I want you guys to tell me in the chat, which rules are more restrictive? Is it easier to get a transaction in a block, or is it easier to get a transaction into a mempool? What do you think? Block or mempool? Which rules are more strict? More strict. Which one's harder? Is it harder to get a transaction in a block, or is it harder to get a transaction in the mempool? Davidson says mempool. Is he right? Mempool, block. A couple of people saying block. Amol says block, even though we just talked about it yesterday, and Amol should know better. So the answer is mempool. And this is how soft forks are able to be deployed on the network. And you can think about it simply like this. In fact, I kind of just gave it away. I didn't quite give it away. Let's say I run a full node, and obviously anything that goes in a block is consensus. Like, you can't argue with block. There's proof of work on it. Like, anytime you see a transaction in a block, there's a certain amount of consensus rules that must be satisfied. In the mempool, we add more rules to that to prevent denial of service attacks. I'm going like this, but really I should be maybe going like this. So if blocks contain this many transactions, the mempool, will have these. So let's say somebody sends a transaction that doesn't pay a fee. There's nothing wrong with that. It could appear you could put that transaction in a block if a miner wanted to put a transaction in a block without a fee. But full nodes will not relay that transaction because that's a potential denial of service vector. So if you create a transaction with no fee, that transaction is allowed in a block, but it is not allowed in basically any Bitcoin full node with default settings mempool. Therefore, mempool rules are more restrictive. It is harder to get a transaction into a node's mempool than it is to get into a block. And just in case you hear these terms later, yes, Davidson wrote the word policy. When we talk about blocks, we use the term consensus. Those are the consensus rules. When we talk about mempool, we call that either policy rules or standardness is another term that you'll hear. If somebody says a transaction is standard or non-standard, that means it either is accepted or not accepted by the mempool rules and the transactions that'll get relayed around the network. All right, 1 minute left. Adi, do you want to wrap it up or?
Yeah, well, this was amazing. I'm sure everyone found it useful. Thank you so much, Matthew, for 90 minutes of your valuable time.
My pleasure.
And we'll share the recording for this one on Discord. Of course, Matthew is in Discord as well. You can ask him questions if you want in one of the channels.
All right, great. To the moon, everybody. Get to work. Let's go.
All right. See ya. Bye-bye.
Bye-bye. Thank you.
Thank you.